we studied how to find the losses of pre-stresses in a pre-stressed concrete beam. Okay, that is one part of this model. Okay. So
Sir, again, screen is not visible, sir.
not visible. Is it same thing for others? Mahesh, Manzoor, Geeta, please confirm whether the screen is visible or not.
Visible, sir.
Okay. Thank you. So we have left with one more part of the second model, that is deflection of pre-stressed concrete members. Okay. So in this session, you will be learning how to find deflection of a pre-stressed concrete member when it is subjected to external load. Okay. When it is subjected to external load. Okay. So you will be learning how to find the deflection of a PSC member for the given loading condition. Okay. Mainly this deflection of a pre-stressed concrete beam depends on several factors. Okay, all the factors which influence the deflection of the PSA beam I have listed out here. You can see imposed load and self-weight. Okay, if the imposed load of the beam or live load on the beam is higher, then we can expect more deflection. And even the self-weight, if you are providing higher cross section to the beam, then the self-weight of the beam increases. If the self-weight increases, it will result in higher deflection of the beam. Then magnitude of the pre-stressing force. Okay, the deflection is also depending upon the magnitude of the pre-stressing force applied. Okay, if the magnitude of the pre-stressing force is higher, then the deflection of the beam is lower. Okay, it's vice versa with respect to pre-stressing force, because I will show you here for pre-stressed force or pre-stressing force. Yes. See, if you are increasing magnitude of the pre-stressing force, what it will do is it will cause the deflection of the beam in opposite direction, like this. In hogging pattern, the deflection of the beam will take place like this. So it will reduce the deflection due to the self-weight and live load of the live load on the beam. Okay. So if you increase the magnitude of the pre-stressing force, then the deflection of the beam, the resulting deflection of the beam will decreases. Okay, because the live load and the dead load. Okay, the live load and the dead load will cause deflection in downward direction. Okay, pre-stressing force will cause deflection in opposite direction, in upward direction. Means it will cause hogging bending moment. Okay, which will result in lesser or reduced deflection of the beam. Okay, then cable profile, it also depends on the cable profile, whether the profile is parabolic or straight or triangular profile. Depending upon the cable profile also, the deflection of the beam will changes. Okay, then second, moment of area of the cross section. Okay, moment of inertia. If moment of inertia is higher, then its deflection will be higher. Okay, because self-weight increases. If the sectional dimensions increases, then moment of inertia will also increases. The increase in moment of inertia will cause higher deflection due to self-weight. Okay, then modulus of elasticity of the concrete, and few more points: shrinkage, creep, and relaxation of stress in steel. Okay, so depending upon all these factors, the deflection of the beam will vary. The span of the member, if the member is very slender, means if the span of the member is very higher, then it will result in higher deflection. Then fixity condition, whether the ends of the beam are fixed or simply supported. Okay, you can see for simply supported beam, the deflection is higher. Okay, so these are all the factors which influence the deflection of the pre-stressed concrete member. Okay, then this deflection can be studied in two steps. Okay, that is short-term deflection and long-term deflection, similar to the losses of pre-stresses. Okay, similar to the losses of pre-stresses, short-term losses and time-dependent losses we have studied, no? Like this, like that. Similarly, we are studying this deflection of the beam for short-term and long-term. Short-term deflection means it is a deflection which occurs immediately after the transfer of the pre-stress on application of loads. Okay, immediately within a short period of time, the deflection that will occur in the PSE beam is called as short-term deflection. Okay, long-term deflection is it is a time-dependent deflection. Okay, it will occur for longer duration. Okay, that is deflection due to creep. Okay, when the beam is subjected to sustained loads for long period of time, what happens? The deflection of the beam will increases. Okay, so we will find the deflection as short-term deflection and long-term deflection. Adding together, you will get the total deflection. Okay, as I said, this long-term deflection, it is a deflection which occurs immediately after the transfer of pre-stress on application of the loads, means at fresh state of the PSA beam. Okay, this deflection will take place. Okay, and this short-term deflection depends on several factors such as span and type of end supports, cross-sectional area of the member, then amount of pre-stressing steel, cable profile, characteristic strength of steel and the concrete. Okay. Depending upon all these factors, the short-term deflection depends. Okay. Then coming to the calculation of short-term deflection, if you take deflection of any pre-stressed concrete beam, there will be three kinds of deflection. Okay. There will be three kinds of deflection. One is deflection due to dead load. Second one is deflection due to live load and deflection due to pre-stressing force. Okay. So while solving the numerical problems, what we will be doing is we will be finding deflection due to dead load separately, deflection due to live load separately, deflection due to pre-stress separately. So we will add all finally to get the total short-term deflection. Okay. Now we will see how to find deflection due to dead load, how to find deflection due to live load, how to find deflection due to pre-stress. Okay. So all of you listen carefully, understand it clearly, students, because the same procedure we will be following for solving the problems. Okay, I will be explaining how to find deflection due to dead load, deflection due to live load, and deflection due to pre-stress. Okay, first we will discuss deflection due to dead load. How to find deflection due to dead load? Okay, dead load means self weight of the beam. Okay, so here we have the formula to find deflection due to dead load. Okay, if the beam is simply supported, okay, if the beam is simply supported, then what we will do is we will find intensity of the self weight. Okay, we will find the self weight of the beam by multiplying cross sectional area with the density of the concrete. Then we will get the intensity of the self weight. Okay, and length of the beam will be given, and if it is a simply supported beam, we will find deflection by using this formula 5 by 384 WL raised to 4 divided by EC into IX, where EC is Young's modulus of concrete, okay, or modulus of elasticity of the concrete. Okay, if the beam is a cantilever beam, okay, if the beam is cantilever beam, one end is fixed, another end is free, then we will find the deflection using this formula WL raised to 4 divided by 8 EC into IX, where EC is Young's modulus of concrete and IX is moment of inertia of the beam. Okay, this is how we find deflection due to dead load. Okay, then coming to the determination of deflection of the beam due to live load. Okay, if the live load given is a UDL, okay, if the live load on the beam given is a UDL of intensity WQ per meter length, then using this formula 5 by 384 of WQ into L raised to 4 divided by EC into IX, using this formula we will find the deflection due to live load. Okay, if the live load given is a point load, okay, if the live load given is a point load which is acting at the center of the span, then we will utilize the formula WLQ by 48. EIX. Okay, EC into IX. Using this formula, we will find deflection due to live load. That is deflection due to point load which is acting at the center of the span. If 2-point loading is given on the problem, okay, if the beam is acted upon by 2-point loads which are placed at 1/3 portion, okay, at 1/3 portion of the beam from either supports, then we have to utilize the formula 23 by 648 into WLQ by EC into IX. Okay. Similarly, if live load given is UDL and the support condition of the beam is cantilever, then you will use WLQ by 3 EI formula, 3 into EC into IX formula for finding the deflection due to UDL when the beam is cantilever. Okay. Sometimes in the problem, the Young's modulus of the concrete will not be given, but characteristic strength of the concrete will be given. If characteristic strength of the concrete is given, utilizing this formula, we will find EC. EC is equal to 5700 root of FCK. Using this formula, we will find the Young's modulus of the concrete. Okay. Suppose if you are not able to remember this formula, okay, 5 by 384, 1 by 80, 1 by 8 WLQ raised to 4 by EI, then 23 by 646. If you are facing any difficulty, if you are not able to remember the formula, we have a generalized formula to find deflection due to the loads. Okay, we have the generalized formula to find the deflection of the beam due to loads, whether it may be dead load or it may be live load, or it may be pre-stressing force, or it may be a pre-stressing force. Utilizing this generalized formula, we can find the deflection. We can find the deflection. Okay. Here below, I have shown one example. One example. See, for example, if you are not able to remember the formula, okay, this formula WLQ by 48 EI into EC into IX. Okay, for the beam subjected to concentrated load at the center of span, the deflection is given by WLQ by 48 EC into IX. If you are not able to remember this formula, you can find it by using this generalized formula. How to find? We have the formula. We have the general formula, that is delta is equal to area into x bar divided by EC into IX. What we will be doing is, we will be writing bending moment diagram for the given loading condition. Okay, we will be writing bending moment diagram for the given loading condition. Then we will consider half of the portion of the bending moment diagram. Okay, we will consider half of the portion of the bending moment diagram. Okay. Using that area of the BMD, we will find expression for deflection by using this generalized formula. Okay, what is that formula? Area into x bar divided by EC into IX. Area means area of this shaded portion. Okay, area of this shaded portion, half of the bending moment diagram, into x bar. X bar is nothing but it is distance of centroid of this area from nearest, from this support, left nearest support, from nearest support, that is x bar. Okay, and EC is Young's modulus and I is moment of inertia. Okay, so you have to find area of this beam BMD, and you need to find expression for x bar, distance of centroid from the nearest support. Substituting, you will get the required formula. Here I have shown one example. Okay, for a simply supported beam carrying concentrated load at the center of the span. See, I have written the bending moment diagram, correct? I have written the bending moment diagram. Okay, what is the maximum bending moment at the center of the span? If the beam is subjected to concentrated load at the center of the beam, it is WL by 4. WL by 4. Okay. Now what I have done? In the next step, I have considered half of the area of the bending moment diagram, half portion of the area of the bending moment diagram. Then utilizing this generalized formula, I have determined expression for this deflection. Okay, where A is area of this shaded portion, area of half of this bending moment diagram. So how much it will be? See, it is a triangle, correct? It is a triangle. Area of triangle is half into base into height, where base is how much? Base width is L by 2 and height of the triangle is WL by 4. It is WL by 4. H is equal to WL by 4. Okay. So half into base into height. I have substituted here half into base width is L by 2 into height is WL by 4. Finally, we will get area as WL square by 16. Similarly, we want x bar value, correct? We want x bar value. But what is x bar? X bar is distance of centroid of this triangle from the nearest support. From the nearest supports, you can see this is a right angled triangle, correct? Huh? For right angle triangle, distance of centroid is 2b by 3. Okay, from this end and from this perpendicular point, it will be at a distance of b by 3. Okay, so here x bar, okay, x bar is equal to 2b by 3. Okay, 2b by 3. This will be 2b by 3, where b is equal to L by 2. Okay, where b is equal to L by 2. Okay, so 2 by third of b, 2/3 of b means b is L by 2. I have substituted here, so you will get 2 gets cancelled. You will get the x bar value as L by 3. Okay, now substitute everything in this generalized formula. Delta is equal to area into x bar divided by E into I. Area is WL square by 8. I have substituted it here. Then x bar is equal to L by 3. Here I have substituted. Okay, area is WL square by 16. Okay, E into I have substituted as it is. Then finally, after simplification, you will get WL by 48 E into I. Okay, the same formula we have here. We have the same formula here. Okay. Okay. Okay, the same formula we have that is WLQ by 48 EI into X. So even if you are not able to remember the formula, you can use this generalized formula to obtain the equation or to do the calculation directly. Okay, I hope you understood, students. Still, if you have got any doubts, you can ask. Okay, this is how we find deflection due to lie load. If you are able to remember the formula directly, no problem. You can directly find, or else you can follow this method. Okay, then coming to deflection due to pre-stress. Okay, now what we learned is we learned how to find deflection due to dead load. Okay, deflection due to lie load. Now we'll study how to find deflection due to pre-stresses. Deflection due to pre-stresses. Okay, now when you are finding deflection due to pre-stresses, the deflection, as we discussed earlier, that depends on the cable profile. Okay, if the cable is straight, then deflection will be different. If the cable is parabolic, okay, like this, the deflection of the beam due to pre-stressing force will be different. Okay, if it is having a triangular shaped profile, then it will be having different magnitude of the deflection. Okay, now we will study, you will take each and every case separately and we will study how to find the deflection. Okay, initially, first right cable, Okay, for a straight cable, situated at a constant eccentricity. Okay, constant eccentricity throughout the length E. Okay, just write the bending moment diagram. Bending moment diagram. See, you can see here, students, this pre-stressing force will cause the hogging bending moment to the beam. Correct? It will cause hogging bending moment to the beam. So here, while writing bending moment diagram, the sign of the BMD is negative. This is very, very important. Remember, okay. For previous cases, the bending moment was positive. Okay, because there we had uh, bending of the beam in downward direction like this. Okay, like this. Therefore, the BMD due to lay load or the dead load was positive, but BMD due to pre-stressing force is negative always. Okay. So what is the total maximum bending moment which will be caused by this pre-stressing force? It is P into E. Okay, P into E is the maximum bending moment caused by this pre-stressing force. Okay, therefore the nature of BMD is also negative. Okay, so here you can see I have used this generalized formula only, area into x bar. I have written the BMD. Okay, so bending moment is constant throughout the length because cable is straight. Okay, it is having constant eccentricity throughout the length of the beam. So bending moment is constant throughout the length of the beam, that is with the intensity of P into E. Okay, don't forget this sign negative for pre-stressing force. So area into x bar. Now I have considered half of the BMD here, half of the BMD I have considered. Then I use this generalized formula, area into x bar divided by EI. Area is what? This height is PE, okay, and length of the rectangle is L by 2. So PE into L by 2 will give area, okay. Then X bar, distance of center of this rectangle from the nearest supports, nearest support. It will be total width divided by 2. Total width is L by 2. L by 2 divided by 2, it becomes L by 4 into L by 4 divided by EI. Finally, the equation is PE square divided by 8EI into X with the negative sign. This is very important. Don't forget this sign. Otherwise, the answer will go wrong. Okay. This is how we find deflection due to pre-stress for a straight cable carrying pre-stressing force of magnitude P. Next, we'll see how to find deflection for a parabolic cable, okay, carrying pre-stressing force of magnitude P. Okay, same, I have used this generalized formula area into x bar divided by EI. See, as a cable profile is parabolic, okay, as a cable profile is parabolic, then the bending moment, nature of bending moment diagram will also vary as parabolic only. It will also vary as parabolic only. The bending moment at the center, eccentricity E. So here at this point we will have maximum bending moment due to pre-stressing force P into E. Okay. So depending upon the cable profile, this nature of bending moment will vary. Here for straight cable, the nature of bending moment was a rectangular shape only, straight only. Here we have the parabolic cable. We will have the nature of bending moment due to pre-stressing force as parabolic nature only, P into E only. Okay. See, again here I have considered half of the bending moment diagram. Okay. Means L by 2 is the base width and height is PE. Okay. Height is PE. So area into x bar divided by EI. Area. Okay. So this is the parabola. Area of the parabola. What is the formula for area of the parabola? What is the formula for area of the parabola? It is area is equal to 2/3 of base into height. This is the area of parabola. 2/3 of base into height. Okay. 2/3 of base is L by 2, height is PE. By this you will get the area, and x bar is, as I said, distance of centroid of this shaded portion from nearest support. Okay. and that value for parabola it is 5 by 8 of b. Okay, x bar is equal to 5 by 8 of b. Therefore, x bar is equal to 5 by 8 of b is what? Base width of the parabola, base width of the parabola, how much it is? L by 2. L by 2. So same thing I have done 5 by 8 of L by 2. Area into x bar divided by a. Finally, we get the equation minus PEL squared divided by 48 EC into IX. Okay, this is how we find deflection due to parabolic cable. Then coming to the deflection due to prestressing force with triangular profiled cable. Okay, so here profile of the cable is triangle. Then similarly, the nature of BMD will be triangular shape only with maximum bending moment at the center as PE. Maximum bending moment at the center as PE. Okay, again I have considered half of the BMD. Okay, for this I have utilized this same formula area into x bar divided by EI. Area of triangle is, see, base width of the triangle is L by 2 and height of the triangle is PE. Half into base L by 2 into height PE will give area, and similarly distance of centroid of triangle from this end is 2/3 of B. 2/3 of B. So 2/3 of B is L by 2. Base width of the triangle is L by 2. Okay, substituting and simplifying, we'll get this final formula as minus PEL squared divided by 12 EI into 12 EC into IX. Okay, the same procedure will continue for the trapezoidal cable. You can see it is a for trapezoidal cable. So at 2 points, the maximum bending moment will be PE. We have to consider half of the portion. Then utilizing, so what we will do is in this case we will divide this area into two areas, A1 and A2. Okay. Then we will find individually the area of individual, that's the rectangle and the triangle and x bar corresponding x1 and x2, x1 bar and x2 bar. Okay, finally by substituting as A1 x1 bar plus A2 x2 bar divided by EC into IX. Using this formula, we will find the deflection due to prestressing force. Okay, so I will explain in detail while solving the problem on trapezoidal profile cable. Okay. Okay, students. Next, we have one special case with respect to parabolic cable. So here in the previous uh, case where we discussed the parabolic cable, here eccentricity at the support is 0. Okay, and at midspan we have the eccentricity E below the central axis. Okay, so we will get some special cases like the cable profile is parabolic with eccentricity E1 above the neutral axis at the support and eccentricity E2 below the neutral axis at midspan. In this case, how to find the deflection due to this parabolic cable with different eccentricities at the support and the midspan. Okay. Here you can see, students, the some part of the cable is above the neutral axis, above the centroidal axis or neutral axis, and some more part of the cable is below the centroidal axis. In this case, the sign will change accordingly. Sign will change accordingly. Okay. So total eccentricity of the cable is E1 plus E2. E1 plus E2 from the center. Okay, total eccentricity of the cable is E1 plus E2. What we will do is we will find deflection due to the the deflection of the parabolic cable, including this overall E1 plus E2. Okay, in that we'll deduct deflection due to this E1 portion, PE1. Okay, so that we'll get the resultant deflection. Okay, see here the portion of the cable for which is above the central axis. This is what the nature of bending moment diagram. P into E1 with the positive sign. With the positive sign. Because why positive sign? The prestressing force. Okay, the prestressing force is above the central axis. Okay, if it is acting above the central axis, it will cause sagging bending moment. So the sign is positive. Okay. Then below diagram represents bending moment diagram due to the combined eccentricity of E1 and E2. Okay. So and it will be negative and it will be negative. So in this combined bending moment diagram, if we deduct this, okay, if we deduct this bending moment due to the pre-stressing force, which will cause bending moment above the central axis, this portion will deduct in this diagram. Okay. So generalized formula is P into E1 plus total eccentricity is P into E1 plus E2. Okay, P into E1 plus E2 with the negative sign. In this, what we'll do, as we have some portion of the cable above the central axis, we will deduct this. Okay, so the resultant will be the net deflection due to parabolic profile cable, which is having some eccentricity at the center of the span and some eccentricity at the support. Okay, this is how we find the deflection for a parabolic cable with different eccentricities at the center of the span and the support. Okay. So here we'll add both. Here you can see, students. Here you can see. So this is the E by I. E into I is the constant. I have taken outside the bracket. So for figure 1, area is PE1 into L by 2. Height is PE1. L by 2 is the base width and height is PE1. So by this you'll get area. Okay. And distance of centroid is L by 4. 1/4. L by 4. X bar is L by 4. Okay. And it is positive sign. And negative sign for second formula, second figure, negative sign. Area is 2/3 of, this is L by 2. 2/3 of base width L by 2 into height is PE into E1 plus E2. Okay, 2/3 of base into height. Into X bar is 5 by 8 of base width, where 5 by 8 of base width is L by 2. 5 by 8 of L by 2. Okay, you will get the resultant deflection. Okay, in the real problem, values will be given, you will get the value, some value for the deflection. Okay, similarly for triangular profiled cable, same kind of calculation we have to do. If the triangular profile cable is having some eccentricity at the support and some eccentricity of the midspan below the central axis, and at support the eccentricity is above the neutral axis. Okay, what we'll do, we'll find total deflection due to E1 plus E2, and then in that we'll deduct deflection due to eccentricity E1. Okay, same procedure we have followed here. Okay. So knowing deflection due to dead load, okay, deflection due to dead load and deflection due to live load and deflection due to pre-stress, adding all together, you will get short-term deflection. Okay, so the short-term deflection is short-term deflection is the sum of deflection due to dead load plus deflection due to live load plus deflection due to pressures. So this is how we find the short-term deflection. Okay. Now coming to the calculation of long-term deflection. Okay. Coming to the calculation of long-term deflection, we have the formula, that is delta IL plus delta IP into Pf by Pi into 1 plus pi, where pi is creep coefficient. Delta IL is deflection due to loads. Deflection due to loads means include that deflection is inclusive of both dead load and live load. Deflection due to dead load and the live load. And delta IP is deflection due to prestress. Okay. And PF by PI is, it is also called as loss ratio. This term is also called as loss ratio. Okay. Where PF is final prestressing force and PI is initial prestressing force. Okay. After some losses, the prestressing force, magnitude of the prestressing force will be reduced. That magnitude of the prestressing forces will be PF. After all losses, final prestressing force divided by initial prestressing force. It is also called as loss ratio. Okay, and pi is the creep coefficient. Every parameter will be given. Okay, in the problem, you need to find the long-term deflection using this formula. Okay. And there are permissible deflection or permissible deflection, the permissible limits which are specified in IS 1343 code book. Upward deflection should not cross span by 300. Okay, and downward deflection which should not cross span by 250. Okay. And why this long-term deflection happens means due to creep. Creep means what? Deflection due to sustained load. Okay, sustained load for long period of time is called as long-term deflection. Deflection due to sustained load for long period of time is called as long-term deflection or deflection due to creep simply. Okay, and it depends on several factors. Okay, the mix proportion and size of aggregates, water cement ratio used in the uh, making of concrete. Okay, type of reinforcement provided, age of the concrete with the time of loading. Okay, and magnitude of the load, and climatic conditions such as humidity and temperature are the things will influence this long-term deflection of the beam. Okay, so this is how we find deflection of the beam. Okay, in the numerical problems, he will give all the details. Cross section of the beam will be given, live load on the beam will be given, amount of prestressing force will be given, cable profile, whether it is straight, parabolic or triangular, profile of the cable will be mentioned. Just you need to find the deflection due to dead load, deflection due to live load, deflection due to prestressing force. Okay, adding all together, you will get the short-term deflection, and using this formula, you will find the creep coefficient is also given. If this long-term deflection needs to be determined, and you just substituting all the values, you will get long-term deflection. If you want, you can also find total deflection by adding this short-term deflection in the long-term deflection. This is how we follow the procedure while solving the numerical problems. Okay. Any doubts, students? Any clarification if needed, you can ask. Okay. Okay, thank you. Now we'll move on to the problem. All of you read this problem. We'll solve a problem now. All of you please write this problem. Read this problem, all of you. Take 1 or 2 minutes time to write the problem. I hope everyone is writing the problem. Is mute the audio. Who's that? All of you go through the problem. Understand the problem. Okay. Then we can solve it by using the procedure whatever I have explained before. All of you go through it and write the diagram for the parameters given so that it will be easy for you to solve the problem. Okay. I have everyone written the problem. Just go through it. A concrete beam having a rectangular section 150 by 300 is pre-stressed by a parabolic cable at an eccentricity of 75 mm at midspan towards bottom and at a eccentricity of 25 mm towards top at support sections. Okay, let me write the diagram for the same. A concrete beam is having rectangular section. Solution. Okay. The cross section is 150 by 300, correct? Cross section of the beam is 150 by 300. 150 by 300. Okay. Pre-stressed by a parabolic cable at an eccentricity of 75 mm at midspan towards soffit or bottom and at an eccentricity of 25 mm at top at support sections. Let me write the central axis first so that we can write the cable profile based on the given problem. Okay, now we go through it. Parabolic cable at an eccentricity of 75 mm at midspan towards of it at midspan. The eccentricity is 75 mm. 75 mm. Okay, then and at an eccentricity of 25 mm towards top at support, towards top, okay, means upward direction, towards top at support 25 mm. Okay, here it is, eccentricity is 25 mm. Okay, so here also same thing, 25 mm. Now you write the cable profile. Okay, so this is what the cable profile. I will call this eccentricity at support as E1, and eccentricity at midspan as E2. E2. Okay, eccentricity at midspan is 75 mm, eccentricity at support is 25 mm. Okay, and it will be carrying some pre-stressing force. The cable. Okay, then moving ahead, the effective pre-stressing force is 350 kilonewton. Okay, effective pre-stressing force is how much? 350 kilonewton. Okay, the beam supports a concentrated load of 20 kilonewton at center of the span in addition to the self weight. Okay, it carries a concentrated load of how much? 20 kilonewton in addition to the sulfate. Okay, sulfate means sulfate will be in the form of UDL. Okay, this is whatever the UDL I am writing, it is sulfate. Sulfate. Okay, intensity of the sulfate. Okay, with a span of 8 meter. Total span of the beam is how much? It is given as 8 meter. Span of the beam is given as 8 meter. Okay, now find the short-term deflection at center of the span under pre-stress, sulfate and live load. Find also the long-term deflection if the loss ratio is 0.8 and the creep coefficient is 1.6 and Young's model of concrete is 38 kilonewton per mm square. Okay, all the parameters needed to do the calculation of the deflection are given. Okay, just you need to follow the procedure which I have explained before. Okay, so before going to solve the problem, you find some basic properties of the beam, that is moment of inertia and dead load of the beam you find. Then we will proceed with finding deflection due to dead load, live load and the pre-stress and long-term deflection. Okay, first you find moment of inertia. Ixx is equal to, it is a rectangle, formula is BDQ by 12. B is 150 into 300 cube divided by 12. Okay, so moment of inertia, if you calculate, you just calculate the answer and check the answer. It is 337.5 into 10 power 6 mm4. Moment of inertia about x-axis. Also find dead load or self weight of the beam. Of beam is equal to, we know that area into density, cross sectional area into density, and cross sectional area is 0.15 into 0.3 in terms of meter into density is 24 kilonewton per meter cube. If you calculate, you will get the intensity of sulfate as 1.08 kilonewton per meter. So sulfate is equal to how much? It is 1.08 kilonewton per meter. Okay. Now what we'll do? We'll find one by one. First one is deflection due to dead load. We'll find. Then we'll find deflection due to live load and deflection due to pre-stress individually. Then we can also find short-term deflection by adding all deflections due to sulfate, dead live load, and the pre-stress. And we can also find long-term deflection. Okay. Now first one, deflection due to dead load. Deflection due to dead load. Okay, deflection due to dead load. So what is the dead load intensity we got? We got it as 1.08 kilonewton per meter. kilonewton per meter, and it's a simply supported beam having a span of 8 meter. Having a span of 8 meter. Okay. So we have the formula for calculating deflection due to dead load. Deflection due to dead load here. What is the formula we have? Deflection due to dead load for a beam carrying UDL, simply supported beam carrying UDL. So here we have the formula 5 by 384 WL raised to 4 divided by EC into IX. Let me copy the same formula. 5 by 384 into WL raised to 4 divided by EC into IX. Okay, where W is dead load intensity, that is 1.08 kilonewton per meter. And EC, how much it is given? EC is given as 38 kilonewton per mm square. 38 kilonewton per mm square. In terms of Newton per mm square, it is 38 into 10 power 3 Newton per mm square. Okay, and length of the beam is given as 8 meter. In terms of millimeter, it is 8,000 millimeter. Okay, and moment of inertia just before we have determined, it is 337.5 into 10 power 6 mm raised to 4. 337.5 into 10 power 6 mm raised to 4. Okay, and W is also calculated before, it is 1.08 kilonewton per meter. 1.08 kilonewton per meter. In terms of Newton per millimeter, it is same only, correct? 1.08 Newton per millimeter. Now you can substitute all the values and you can get the deflection due to dead load. Therefore, deflection due to dead load is equal to 5 by 384 into load is 1.08 into length of the beam is 8,000 raised to 4 divided by EC into IX, 38 into 10 power 3 into 337.5 into 10 power 6. Okay. By this you will get the deflection due to dead load. All of you please calculate. Please work out the problem. Don't simply listen to the class. Take the book, pen, calculator and solve this problem. Okay. And cross check your answers. If you get any doubts at any point of time, you can interrupt and you can ask the doubts. Okay. Or else if you are getting any other different answers, let me know. Okay. We'll correct it and we'll move ahead. Okay. Now, if you calculate the deflection due to dead load, you will get it as 4.49 millimeter. All of you check your answer. Check your answer. It is 4.49 millimeters. To this calculation of deflection due to dead load is over. Okay. Similarly, we will calculate deflection due to live load now. Second, deflection due to live load B. Deflection due to live load. Okay. Just go through the problem. The live load intensity is how much? It is a point load, 20 kilonewton load acting at the center of the span. Let me write the diagram again. Point load, 20 kilonewton, 20 kilonewton, 8 meter span. Okay. Now, what is the formula we have for a point load carrying, as for a beam, simply supported beam carrying point load? Let me go to deflection due to live load. See here we have the case. This is second case. Okay. The formula is WL cube divided by 48 EC into IX. Let me copy the same formula. Delta is equal to, okay, deflection due to live load is equal to WL cube divided by 48 EC into IX. Okay, where W is equal to here 20 kilonewton. In terms of Newton, it is 20 into 10 power 3 Newton. Length is 8000 and ECI, everything is not just substitute. So delta LL is equal to 20 into 10 power 3 into length of the beam is 8000 cube divided by 48 into 320 into 10 power 3 into 337.5 into 10 power 6. Sorry. This EC is 38, correct? 320. 38 into 10 power 3. Okay. By this, we'll get deflection due to live load. Calculate the answer and check your answer. It is 16.63 mm. It is 16.63 mm. Okay. To this, deflection due to live load is over. One more type of deflection is remaining, which is that it is deflection due to prestress. Third one, C. Deflection due to prestress. Okay, deflection due to prestress. Okay, that is delta PS. Okay, now to calculate deflection due to prestress, we just look into the cable profile. How is the cable profile here? It is having some eccentricity at the support and some eccentricity at the midspan. I'll go to the case where I'll go to the notes here. Deflection due to prestress. No, yes. So this belongs to this case. Yes, here it is belong to this case. Okay, it is having, this cable is having some eccentricity at the midspan and some more eccentricity at the support. Okay, now nature of BMD is what? This is what the nature of BMD. Okay, plus PE1 and minus with negative sign minus P into E1 plus E2. Let me write the diagrams here. So we will utilize this generalized formula. Okay, that is area into x bar divided by EC into IX to calculate the deflection due to prestress. Okay, now I am writing the minimum diagram for the prestressing force which is existing above the central axis. Okay, this will be positive sign here. P into E1. Okay, prestressing force P is given. How much it is given here? 350 kilonewton. 350 into 10 power 3 Newton. Okay, P is equal to 350 kilonewton. Nothing but 350 into 10 power 3 Newton. And eccentricity E1 at the support is how much? E1 is equal to 25 mm and E2 is equal to 75 mm. E1 is equal to 25 mm and E2 is equal to 75 mm. Okay, so P into E1 is 350 into 10 power 3 into 25. Okay, so you'll get the answer as 8.75 into 10 power 6 Newton millimeter. It's a moment, correct? P into E1. Okay. Now, one more nature of bending moment diagram. P into E1 plus E2 with parabolic bending moment diagram. P into E1 plus E2. Okay, here it is P into E1 plus E2. Okay, that is 350 into 10 power 3 into E1 plus E2. E1 is 25 plus E2 is 50. So we'll get the answer as 35 into 10 power 6 Newton millimeter. Okay. Here, what is the sign? Very important. Sign is negative. Negative. Okay. Positive and negative. Here you can see some portion of the cable is above the central axis. Okay. For that, sign is positive. P into E1. That's it. P into E1. And so portion of the cable is below the central axis. Negative sign. Okay. Negative sign means it will cause hugging bending moment, as I said before. So negative sign P into E1 plus E2. Okay. Now we'll utilize this formula. Delta into area, and delta is equal to area into x bar divided by EC into IX. Okay. So we know that delta is equal to area into x bar divided by EC into IX. Okay. Now you divide this BMD into half portion. Okay. Okay. This will take as rectangle number 1. This will take rectangle number 1 and this will take parabola number 2. Component 1 and component 2. Okay. Now we will elaborate this generalized formula according to this case. Okay. Here we have 2 components. So if we elaborate this, it will be area into x bar A1 into x1 bar. Okay. So here we have plus sign. I'll take the same sign here, plus A1 into x1 bar. Here we have negative sign, minus A2 into x2 bar all divided by EC into IX. Okay. Now we'll find each and individual area separately. Okay. So here this height is how much here? 8.75 to 10 power 6. 10 power 6. and this length is L is equal to 8 meter. Okay, it is 4 meter, 4 meter, and 4000 mm. If you convert it into mm, this length, half of the span. Here also it is 4000 mm base width. Okay. Now area one, area of rectangle one, A1 is equal to, from figure, A1 A1 is equal to, see, area of rectangle is width into height 4000 into 8.75 into 10 power 6, correct? 4000 into 8.75 into 10 power 6. By this we'll get the area 1, okay, as 3.5 into 10 power 10 mm square. Then x1 bar. X1 bar means what? X1 bar means distance of centroid of component 1 from nearest support. This is x1 bar. How much it will be? Total length divided by 2, 4000 divided by 2. 4000 divided by 2. Nothing but 2000 mm. Then A2, area of component 2 means area of parabola. Okay. We have the formula for finding the area of parabola, that is 2/3 of base into height. 2/3 of B into H is the formula. 2/3 of B is how much? 4000, and height is 35 into 10 power 6. 35 into 10 power 6. So by this we will get E2 as 9.33 into 10 power 10. Please cross check the answer. Then x2 bar we want. x2 bar. x2 bar means what? It is distance of centroid of component 2 from nearest support. This is x2 bar. Okay. So for x2 bar we have the formula, that is 5 by 8 for parabola. Okay. For parabola it is 5 by 8 of B. Okay. It is 5 by 8 of B. 5 by 8 of base width. Therefore 5 by 8 of base width is 4000. So you will get the answer as 2500 mm. Okay. Now every parameters are calculated. Just substitute all the parameters into this equation. You will get deflection due to prestressing force, that is delta PS. Therefore delta PS is equal to A1 x1, that is 1 by EC into IX, 1 by, or else A1 x1, A1 is 3.5 into 10 power 10, 3.5 into 10 power 10 into x1 is, x1 bar is 2000, then minus A2 x2 bar minus 9.33 into 10 power 10 into x2 bar 2500 whole divided by EC into IX. EC is 38 into 10 power 3 and Ix is 337.5 into 10 power 6. Okay. By this we will get deflection due to prestress. Okay, if you calculate the answer, you will get the answer as minus 12.73 mm. Why you are getting minus sign, students? Because it will cause the deflection in opposite direction. That is why the sign you are getting negative. Okay. Now you got deflection due to dead load. You got deflection due to live load. Deflection due to prestress. You can easily calculate short-term deflection now. Therefore, short-term deflection is equal to sum of deflection due to dead load plus deflection due to lay load plus deflection due to pre-stress. Okay, deflection due to dead load is how much? 4.49 plus 16.63 minus 12.73. 4.49 plus 16.63 minus 12.73. So by this you will get the answer as 8.39 mm. Okay, you will get the answer as 8.39 mm. Okay. So short-term deflection is 8.39 mm. So final answer you are getting with positive sign means final deflection due to short-term, the final short-term deflection will be in downward direction only. Okay, means it will be in, let me show the direction, downward direction, 8.39 mm. Now, I hope this calculation is clear for everyone. Still, if you have got any doubts, you can ask. Now we have calculated short-term deflection. Similarly, we will calculate the long-term deflection. Okay, in the problem, it is also asked to find long-term deflection. Correct? Okay, find the short-term deflection. Okay, at the center of the span. Then also the long-term deflection we have to find. Okay, write the shaded line as long-term deflection. Okay, long-term deflection. Long-term deflection. Okay, so let me copy the formula of long-term deflection. What is the formula? The final deflection or long-term deflection is equal to delta IL plus delta IP into PF by PI into 1 plus pi. Delta is equal to delta IL plus delta IP into PF by PI means final pre-stress divided by initial pre-stress. Okay, into 1 plus pi. Okay, now we just go through the problem. Loss ratio is given as 0.8 and creep coefficient is given as 1.6. Okay, first we will find one by one. Where delta IL is what? It is deflection due to loads. Deflection due to loads. Nothing but deflection due to dead load and the deflection due to dead load and lay load. Okay, deflection due to dead load is 4.49 and deflection due to lay load is 16.63. So you will get the answer as 21.12 mm. And delta IP is deflection due to pre-stress. That is delta PS that we have already calculated. We got it as delta PS minus 12.73 minus 12.73 mm. Then he has given loss ratio directly. Loss ratio is 0.8. Okay, loss ratio means this ratio of this PI by PI only. Okay, loss ratio nothing but PF. So the ratio of final pre-stress to that of initial pre-stress is called as loss ratio. It is directly given 0.8, and creep coefficient is also given. Creep coefficient, creep coefficient pi, it is given as 1.6. Okay, now we can substitute everything to get the long-term deflection. Delta is equal to delta IL is 21.12 plus delta IP is minus 12.73. Let me change the sign here. Minus 12.73 into loss ratio 0.8 into 1 plus pi, 1 plus 1.6. By this we'll get short-term deflection. Delta is equal to 28.41 millimeter. This is the long-term deflection. Okay, so to this the problem gets completed. If you have got any doubts at any point of calculation, you can ask students. Any clarification is needed in this calculation? Any clarification needed? Thank you. So we'll move on to the next problem. All of you please write the next problem. Write this problem, students. Take 1 or 2 minutes time. Okay, we'll start this problem now. Go through the problem. A rectangular concrete beam of cross section 150 by 300 mm is simply supported over a span of 6 meter, and it is pre-stressed by means of symmetric parabolic cable at a distance of 120 mm from bottom fibers at support section and at a distance of 60 mm from bottom fibers at midspan section. We will write the diagram. Solution. It's a rectangular beam of rectangular section. Cross sectional dimensions 150 by 300. Mm. Write the central axis. Okay, now go to the cable profile. Just see how the cable profile is given. It is prestressed by means of a symmetric parabolic cable at a distance of 120 mm. Okay, 120 mm from bottom fibers at support section. Okay, the cable is at a distance. Total height is how much? Total height is 300 mm. Total height is 300 mm. Okay, so if total is 300 mm, so this length, height of central axis will be at a distance of 150 mm. Okay, you just go through the problem. He says that prestressed by means of a symmetric parabolic cable at a distance of 120 mm from bottom fibers at support. Okay, so at support, cable is at a distance of 120 mm from bottom fiber. Okay, here also same thing, 120 mm. Okay, at support. Then, and at a distance of 60 mm, 60 mm from bottom fibers at midspan. At midspan from bottom fiber, it is at a distance of 60 mm. This is 60. Okay, so he says that it is a parabolic cable. Let me join the points now. Okay, so this is 60 mm. 60. I hope you are understanding. The initial prestress in the cable is 300 kilonewton. Prestress in the cable is given. It is given as 300 kilonewton. kilonewton. Okay, determine maximum deflection of the beam at transfer. Central concentrated force to be applied to nullify the above deflection. Okay, we'll solve one by one. Now, here you can see the full cable profile is below the central axis only. It is below the central axis only. Let me join the endpoints of the cable now. Now I am joining endpoints of the cable. The full cable is located below the central axis, correct? Okay. Now what I will do, I will take here eccentricity as E1. E1, here eccentricity as E2. Okay, this E1 is equal to how much it will be? How much it will be? See, from here to here it is 150. 150 minus this 120 will give E1. It will be how much? 30 mm. Okay. Similarly, what about the E2 value? E2 value, eccentricity E2. From here to here we have 120 mm. 120 minus this 60 will give E2. That is 60 mm. 60 mm. Okay. So this completes the writing of the figure. If you want, you can show the calculation here. This E1 is equal to 150 minus 120, 30 mm, and E2 is equal to 120 minus 60, 60 mm. Okay, so both eccentricity are below the neutral axis only, below the central axis only. Correct? Okay, both the eccentricities are below the central axis only. Okay, then pre-stressing force is given. It is given as 300 kilonewton. P is equal to 300 kilonewton. Nothing but 300 into 10 power 3 Newton. Then Young's modulus of concrete, it is given as 3.8 into 10 power 4 Newton per mm squared. This is what the given data. Okay. What is the question here? Maximum deflection of the beam at a transfer. This is the first question. Maximum deflection of the beam at a transfer. Okay. Then central concentrated force to be applied to nullify the above deflection. First we will solve this first question. Okay. Maximum deflection at a transfer. At a transfer means what? At transfer condition, there will not be any live load. Correct? Because still the PACB is at its manufacturing state during the transfer of prestresses. Correct? So during the transfer of prestresses, there will be only two forces. One is self-weight of the beam and prestressing force. Okay. So if he says to find deflection at transfer, you need to find deflection at self-weight and deflection due to pre-stressing force. Adding together, you will get deflection at transfer. Okay. Now, question one. Question one. Deflection at transfer. This we'll find. Okay. So deflection at transfer is given by deflection at transfer is equal to deflection due to dead load plus deflection due to pre-stressing force. Now we will find deflection due to dead load A. In that A, deflection due to dead load delta DL. Okay, we have to follow the same procedure whatever we have followed for the previous problem. Okay, dead load of the beam, first you find it. Dead load of beam is equal to cross-sectional area divided by density. Okay, cross-sectional area is how much? It is 150 by 300, nothing but 0.15 into 0.3 into 0.3. The density is 24. Okay, by this we'll get intensity of load as 337.5 into 10 power 6 Newton per kilonewton per meter. Sorry. Answer is different. So we'll get the answer as dead load as 1.125. One more thing here. Density of the concrete is given as 25 kilonewton per meter cube. Na? So we will consider 25. In the absence of the data, we will assume it as 24. We will take it as 25 only here. By this, we will get self-weight of the beam. If you calculate, you will get the answer as 1.125 kilonewton per meter. In terms of Newton per millimeter, it is 1.125 into 10 power 3 Newton per millimeter. Okay. Now, we have the formula for calculating deflection due to self-weight of the beam. We know that delta DL is equal to, what is the formula? It is 5 by 384 WL raised to 4 divided by EC into IX. So intensity of the dead load is W is known 1.125 into 10 power 3. W is equal to 1.125 into 10 power 3 Newton per millimeter. Length of the beam is given as how much? Length of the beam, it is 6 meter. 6 meter. L is equal to 6 meter. In terms of mm, it is 6000 mm. EC is given as 3.8 into 10 power 4 Newton per mm square, and moment of inertia you can calculate PD cube by 12. V is 150 into 300 cube by 12. So sectional dimension is same as that of previous problem. Answer is same, 337.5 into 10 power 6 mm 4. Okay. Now we can get the deflection due to dead load. Therefore, delta DL is equal to 5 by 384 into W is 1.125 into 10 power 3 into 6000 raised to by EC 3.8 into 10 power 4 into IX 337.5 into 10 power 6. Okay. Therefore, delta DL, if you calculate, you will get the answer as 1.48 mm. Please check the answer. Okay. Now we have calculated deflection due to dead load. Now we will calculate deflection due to prestress. B. Deflection due to prestress. Deflection due to stress. Okay. So it is also a parabolic cable having different eccentricities at the support and the midspan. Correct? Huh? Now write the diagram. So this is a cable profile having different eccentricities at the support and the midspan. Same case will come here. Here also same case. There is one minor change. I will tell you. First, write these two. Copy these two figures. Okay. Copy these two figures. These are a bending moment diagram. Here it is P into E1. Here it is P into E1 plus E2. Okay, pre-stressing force, how much it is given? Pre-stressing force 300 into 10 power 3 Newton, and E1 is 30, E2 is 60. 300 into 10 power 3 into 30. So you will get the answer as 9 into 10 power 6 Newton millimeter. So here P into E1 plus E2 is 300 into 10 power 3 into E1 is 30 plus E2 is 60. Okay, we will get the answer as 27 into 10 power 6 Newton millimeter. Okay, see here you can see students. So for top diagram the sign is positive, for bottom diagram sign is negative. Why the sign is positive for top diagram? Here the cable, the eccentricity E1 is above the centroidal axis, that is why sign is plus. Okay. For the bottom portion of the cable, eccentricity E2 is below the central axis, sign is negative. That is why sign is negative. Here in this case you can see, students, at support also E1 is also below the central axis, E2 is also below the central axis. Okay, if the eccentricity is below the central axis, sign should be what? Negative. So here for both the diagrams, the sign is negative, very important. Okay, that sign depends on whether the eccentricity is below the central axis or above the central axis. If the eccentricity is above the central axis, then sign is positive. Below the central axis, sign is negative. So here for E1 and E2, both E1 and E2 are below the central axis. Therefore, both the signs will be negative. Okay, this is what the change that we can see in this problem. Okay, write the central axis now. Rest of the calculation remains the same as we calculated for the previous problem. Same way we have to calculate here using that area into x bar divided by EC into Ix formula. Okay. Total length of the beam is 6 meter. 6 by 2. Length is given as 6 meter. Okay. 6 by 2 is 3 meter, means this becomes 3000 mm length. Here also 3000 mm. Okay. Here height is how much? 9 into 10 power 6. Okay. Here we have height as 27 into 10 power 6. Okay. Both are negative. Both are negative. Negative and negative. So we have the generalized formula to calculate the deflection. Therefore, deflection due to prestress is equal to area into x bar divided by EC into Ix. So you can elaborate this formula with respect to our case. Here we have two components, rectangle 1 and parabola 2. Two components. Okay. With respect to rectangle 1, area into x bar is A1 into x1 bar. What about the sign? Sign is negative. Negative sign. That means this EC into Ix will be common. First we will take that common. 1 by EC into Ix into here for component 1 sign is negative minus A1 into x1 bar. For component 2 also sign is negative, again minus A2 into x2 bar. Okay. Now you find A1 x1 bar and A2 x2 bar. Therefore A1 bar is equal to height is 9 into 10 power 6, base width is 3000. Therefore 3000 into 9 into 10 power 6. If you calculate, you get the A1 value as 2.7 into 10 power 10 mm square, and x1 bar. What will be the value of x1 bar? What is x1 bar here? Distance of centroid of rectangle 1 from nearest supports. It is b by 2. Nothing but x1 bar. So b is 3000. X1 bar is equal to b by 2. B by 2, nothing but 3000 divided by 2, 1500 mm. Then A2 is equal to area 2 is equal to, it is a parabola. Formula for finding the area parabola is 2/3 of V into H. 2/3 of V is 3000 into height of parabola is 27 into 10 power 6. 27 into 10 power 6. By this, you will get the area of parabola, that is 5.4 into 10 power 10 mm square. Okay. Then you find x2 bar. What is x2 bar? x2 bar is distance of center of component 2. This is x2 bar. Okay. From nearest support. So formula for x2 bar is 5 by 8 of b. 5 by 8 of b. 5 by 8 of 3000. You will get the answer as 1875 mm. Okay. Now substitute everything in this equation. You will get the deflection due to prestress. Therefore, deflection due to prestress is equal to 1 by EC into IX. 1 by EC is how much? It is given as 3.8 into 10 power 4 into IX is 337.5 into 10 power 6 into A1 x1 plus A2 x2 bar. A1 is minus, okay, minus A1 x1 bar 2.7 into 10 power 10 into x1 bar is 1500 minus A2 x2 bar. A2 is 5.4 into 10 power 10 into x2 bar is 1875. So by this you will get reflection due to prestress. You will get it as minus 11.05 mm. Minus 11.05 mm. This minus sign indicates deflection is in upward direction. Okay. So this is in downward direction. Now it is asked to find deflection at transfer, which is nothing but deflection due to dead load and prestress. Therefore, below you write, therefore, maximum deflection at transfer condition, which is nothing but deflection due to dead load plus deflection due to PS prestress is equal to deflection due to dead load is 1.48 mm. 1.48 mm. Prestress is minus 11.05. So you will get the answer as minus 957 millimeter. Okay. So to this we have solved the first question. Now moving on to the second question. We have to determine central concentrated load. Central concentrated force to be applied to nullify the above deflection. Above deflection means deflection at transfer. Okay. Above deflection means deflection at transfer. Okay. Means what is the deflection? We have got minus 9.57 mm. Second question, what we have to find is second question, central concentrated force. Determination of central concentrated force to nullify above deflection. Okay. So during at the transfer condition, what is the deflection? It is minus 9.75 mm. Okay, minus indicates the deflection is means sagging bending moment in upward direction. Okay, so here we have the deflection of how much? 9.57 mm. Okay, now the question is to nullify this deflection. Okay, to nullify this deflection, we have to find central concentrated load to be applied at the center of the span. Okay, means the deflection due to this load, when it becomes equal to deflection at this transfer, then the beam will be in static condition. It will not undergo it will be in straight condition. This is what the problem. Okay. Therefore, to nullify above deflection, when deflection due to nullify, write a sentence, to nullify above deflection, that is 9.57 mm, following condition must be satisfied. Must be satisfied. What is that condition? If the deflection due to lay load becomes equal to deflection at transfer, it will get nullified. The total deflection becomes nullified. Okay. This is what the condition. Okay. What is the formula for deflection due to lay load? He says that it is a central concentrated load. For central concentrated load, we have the formula as WL cube by 48 EI. Correct? So WL cube divided by 48 EC into IX must be equal to how much? It is 9.57 mm. 9.57 mm. Okay. So only W is the unknown. Rest of the parameters are known. Just substitute and we will get the value of central concentrated load to be applied to nullify the deflection of 9.75 mm. 9.57 mm. So W we keep as it is. Length of the beam is 6000 mm. 6000 cube divided by 48 into EC is 3.8 into 10 power 4 into IX is 337.5 into 10 power 6 is equal to 9.57. Only W is the unknown. You can solve for W now. So you will get the answer as 27.27 into 10 power 3 Newton is equal to 27.27 kilonewton. Okay, so if you apply a central concentrated load of 27.27 kilonewton, then this deflection due to pre-stress and the dead load will get nullified. So the beam will be in static condition. Okay, so to this this problem is over. If you have doubts at any point of calculation, you can ask students. Any doubts here in this problem? I hope this is clear for everyone. Okay, so to this we'll start the class today and we'll continue in the next class. Okay, thank you all.